This is an example of a non-homogeneous higher order equation. This is because we have here a certain value for our right hand side not equal to 0. Hence, this can be represented by any g of x. And since g of x is any constant, and as you return that on the right hand side, the given equation will no longer be homogeneous. The point here is, if this is homogeneous, we had the process presented in the previous videos and previous discussions. But since it's a non-homogeneous equation, we are going to use a separate method in solving for this. The general solution for a non-homogeneous higher order equation is expressed in this manner. Y, it's still y because we have here our dependent variable y here, is equal to y sub c plus y sub p. Y sub c is what we call as our complementary solution that we were able to use before if our g of x here is equal to 0. So we're going to treat our right hand side be equal to 0, forgetting minus 3 in the meantime. We're going to solve for y sub c using the same process, the process involving auxiliary equation, and if the roots are distinct and real, or repeated, or imaginary and repeated, we will have different general forms of our solution. So please take note of that and kindly review those processes. As for y sub p, this is added since our equation is non-homogeneous. It's called the particular solution of the equation. And please be guided with this table of trial particular solution presented here. Since our g of x is constant, we are going to use here the representation on our first item for any constant. Our y sub p is any a. But since we need to be exact with the value of a, we're going to use a specific process later on to solve for the value of this a. So we'll have it later. So first, let's start solving with y sub c, or the complementary solution of the given equation, assuming that our g of x is equal to 0. Hence, we can treat this into an equation with the differential operator d in this manner. You have f of d of y equal to 0. Hence, you will have here d squared. Take note, we are factoring y, so this would become minus 1. Then you have here y is equal to 0. Okay, don't forget about that because this will only be d if we have the first degree order of derivative. Okay, so with that, we can come up now with our auxiliary equation in this manner. You will have m squared minus 1 equal to 0. Let's solve for m, and then later on, let's identify if they are real and distinct, etc., etc. Of course, this is a perfect, it is a difference of two squares. So you could have here m minus 1 times m plus 1 equal to 0. Hence, your first root is equal to positive 1, and your second root is equal to minus 1 or negative 1. Or, of course, you could always interchange them. Now we can see that our roots are real and they are different from one another. Hence, we are going to use the specific general solution for our equations having distinct and real roots. Again, take note, this is for y sub c process. So our y sub c must follow general solution for distinct and real roots following this item. You have c sub 1 e to the power of m sub 1x plus c sub 2 e to the power of m sub 2x. Take note, we just have two terms because we only have two distinct roots. Okay, and at the same time, we are going to substitute here our roots. So you will have here y sub c is equal to your c sub 1 e to the power of your first root 1x plus c sub 2 e to the power of your second root negative 1x. Or you can simplify it in this manner: c sub 1 e to the power of x plus c sub 2 e to the power of minus x. This is for your y sub c. Okay, so we already did that as well. We have a lot of examples doing this type of process before. Kindly review those previous videos. This time, this is not the exact solution of our equation here because we still need to look for y sub p. As mentioned earlier, y sub p is equal to constant or any constant a, as this is what the table presented to us earlier. The next step here in solving for y sub b is looking into our equation. Our equation, the highest degree or second degree of derivative is second degree. So we can have, let's take the first order derivative of y sub b. And since a is constant, the first order derivative of that is 0. Then we go to the second order derivative because that matches our highest degree here, still 0. We'll be using this as we are going to substitute this on our equation. So instead of y double prime minus y is equal to minus 3, we are going to substitute y double prime of p for y double prime and y sub p for our y here. Since there's no first order derivative, we will not be using this in the meantime. So here's how it goes. This is for our y sub p process. So your first order derivative is this here, 0 minus your y sub p is equal to is a, and then you have here equal to negative 3. Okay, this was the original equation, and this is the particular solution or equation using these ideas presented. Hence, we'll have here minus a is equal to negative 3, so a is just equal to 3. So now that we have that, what was our y sub p earlier? Our y sub p is just equal to a, hence our y sub p is just equal to 3 as well, as this is the value of a. Now, we have y sub b, we had y sub c earlier. We can now present the final solution of this given equation in this form. So our solution, y is equal to y sub c plus y sub p. Our y sub c is this here. So you'll have this one here. Okay? So you will have c sub 1 e to the power of x plus c sub 2 e to the power of minus x plus your y sub p is just equal to 3. This is the solution of the given equation where it's non-homogeneous and we're able to construct our y sub c and y sub p as they are the components of our general solution. So that's the exact process on solving non-homogeneous equations. We're only going to differ as to the ideas here on our table, because this patterns on our g of x being a constant, but if it's not, we'll have a different form, but still the same processes to be followed. Thank you very much for watching.